All right, so let's take a look at the next problem, which is 4. So we're given another set of differential equations here and of order 5. So let's go ahead and rewrite this using the R. So that's called the characteristic equation. So let's do that. So R to the power of 5 minus 15R, or R minus 125 equals to 0. So this, after we factor, and again, I would graph this just to see where the asymptotes are to help me with the factoring process. But after factoring this out, it looks like R minus 1, R minus 5 squared, and R squared minus 4R plus 5 equals to 0. So this one has a good mix of, I guess, all type of possible solutions. So from the first factored out, we get R equals to 1. That's a whole number. And from this second part, we get R equals to 5, keeping in mind that this has a multiplicity of 2, and that's multiplicity of 1. And from this, you can use the quadratic formula to solve for R, which gets you that, I got 2 plus minus I. And this one has the multiplicity of 1. All right, so just remembering what we did for all of these solutions for the second order differential equations. It's C1 e to the power of t. This solution, that term is coming from this first solution, plus C2 e to the power of 5t. This would be done if we had a multiplicity of 1, but since we had 2, we have to add one more term to it. So C2 t e to the power of 5t. Okay, and the next parts, we're going to have the sine and cosine mix that's coming from this. So we're going to have C4 e to the power of 2t cosine of t plus C5 e to the power of 2t sine of t. And there we go. This is our solution for number 4. Just to practice a little more, if we had maybe 2 power of 2 here, then this multiplicity would change to 2. Then all we have to do is just add, I guess, 2 more terms. C5 e to t times t cosine of t plus 5 is used, so c to the power of 6. Not power, but c6. And c7 e to the power of 2t, t sine of t. So we just add, and you get the picture. I think you, as the multiplicity increases, you just have to add on those more terms. All right, so let's take a look at the next problem. This problem is now we're tackling on something very similar to what we've been doing for the past 2 weeks, which is the solving of the non-homogeneous differential equation. So far we have all done all these problems are homogeneous because they end in at 0. But let's see what happens if we are solving for the non-homogeneous problems. Okay, so all right, so let me rewrite this in the characteristic equation. So that would be using R. Minus 12R squared plus 48R minus 64. And if you remember from the last 2 weeks, we first treat this as 0 to find the complementary solution. All right, so we kind of deal with the left-hand side and the right-hand side separately. From this equation, this can be factored out as R minus 4 cubed equals to 0. So this means that R equals to 4, and this has the multiplicity of 3. So we can conclude that the complementary solution of t This is C1 e to the power of 3t. And remember, this has multiplicity of 3, so we need two more terms. C2 e to the C2t e to the power of 3t plus C3 t squared e to the power of 3t. All right, so we're done with the left-hand side. Now we have to take a look at the right-hand side to come up with the particular solution. If you remember the table of our of different types of particular solutions that we can take for our guessing, just from the look, we don't really care. Well, this one is just the constant, so I guess it's just going to be A. And from this, that's going to take on the form of b e to the power of negative 8t. And from this, that's going to take c to the power of e to the power of 4t. All right, so we come across a slight so sorry, I seem to have made mistakes here. I was wondering okay, so these should be 4 because our R value is 4, and this just means it's multiplicity, so that should not take in a role. Sorry about that. Okay, so here is our problem. We have those two repeating, and generally that's not good because in the end, if we have the same repeating terms, then it's just going to cancel each other out. So, I mean, if you forget to notice that, as you solve by plugging these in, you will quickly find out that it doesn't work. Something doesn't look right. Either you're going to end up with 0 equals to 0, or something that doesn't work, like maybe 1 equals to 0. Okay, so in that case, what you do is you have to go back and check our multiplicity is 3, which means this has we can add not t squared, but we're going to have to add the next term, which is t cubed. Okay, so this is actually it. This is our guess or the particular solution, and this is our complementary solution. Okay, and number 6 is now find a general solution to problem 5. I'm gonna leave this problem up to you guys because it's just a lot of plugging in. You would have to obviously take differential of these equations 2 times first time, and plug it all in accordingly, and to solve for these A, B, and C's. I'll tell you the answer. If you do that, you should get the following answer. So the answer to number 6 is, we're just I guess copying the complementary solution. And the A is negative 3 over 16. B is 1 over 54. And finally, our C is 1/3. Okay, so again, you should get this after you take different differentials and plug it into our equation. That should be the general solution for number 5.